exploring based on motion vision, bridging the paradigm gap between manual analysis and automated system. This is my render. First, I introduce the background and clarify the core problem, why this work matters. The CDBT relies on international monitoring system to detect nuclear explosions with 4 fundamental technologies: seismic, infrasound, hydroacoustic, and radionuclide. My research focuses on seismic and infrasonic technology. So far, the grand challenge remains automatically, rapidly, and efficiently identifying the nuclear explosion from natural source or background noise. There lies a gap between automated processing and manual analysis. On one hand, current state-of-art automated system rely on one-dimensional signals techniques, such as STA to LTA, or PMCC, or slowness-based triggers, wavelets transform, and handcrafted feature extractions, and traditional motion learning classifiers. This kind of techniques cannot capture the intuitive patterns that experts recognize. On the other hand, human analysts depend on eyes or vision to identify contextual or subtle shapes to distinguishing the signals. So there is a paradigm gap between manual analysis and automated processing. Our innovation. Our solution is ally. Our solution is ally AI with how experts actually do. Since human experts depend on AI to do the analysis and identifying work, we can teach AI to do the same work. To turn this idea into actionable pipeline, we set up a 4-step framework. First, step one is signal processing and magnification. At the pre-processing stage, First, we eliminate the breakpoint and treat the signal to straighten out the experimental or environmental trees. Then apply the bandpass filters. At last, normalize the signal because one image has limited width and height. After do this, we perform magnification. We confirm processed signals into two types of images. One is simple version, just a waveform plot. It is faster for the algorithm. Another is a spectrogram, such as wavelets transforms, version. But it is good for experience the features such as infrasound. But it is much more time consuming. Step 2, dataset construction and annotation. A robust computer vision or AI model needs higher quality labeled dataset. So we built a dataset tailored to nuclear exploration monitoring. We collected many signals, including atmosphere and underground nuclear exploration signals. There is a problem because nowadays no country dare to conduct atmospheric nuclear test. It is a challenge. It is a challenge to infrasonic research area researchers. We have not enough data to learn the features. Our solution is, please examine the two group signals. The upper signals from one of the channel of upper signals from one of the atmospheric nuclear exploration from China. And this group signals from applied exploration. We can see these two group signals are identical in appearance. So I insist on that we can use the applied exploration signals to verify our infrasonic technologies, including hardware and software. In the following chapters, all the work we use applied exploration signals instead of nuclear exploring signals. And we collected a lot of other natural source signals. This is a microbar measured by our experimental array. And this is mountain waves. Okay, step 2. Step 2, annotation. Annotation very important. During the work, we tried all kinds of labeling. Different labeling leads to different results. For seismic work, for seismic signals, we label explosion or earthquake or P waves or S waves, and sub-type labels. For infrasound signals, we label explosion, that is polarized explosion. And other natural source, background noise. Critically, each bounding box defines two things: the signal's class, even explosion or earthquake or other natural resource, and P waves, S waves, I waves, and its exact time window, start and time. This is essential to later localization. Okay, step 3. AI model select and training. Here, in my research work, we select Euro V11. Why we use this model? As we all know, there are a lot of AI models. First, it is a single stage detectors. So, it is extremely fast and efficient. Second advantage, higher accuracy. And it is a molten object detector. It can identify multiple signals. For example, P waves, S waves, earthquake, or explosion in a single image, unlike some one-dimensional methods that struggle with overlapping phases.
The time is 20.
Yeah.
This is the architecture of the Euro 11. How to train the models? We labeled 5 classes: P waves, S waves, explosion, earthquake, infrasonic waves. Of course, we can label more. And the output of the model is have 3 pieces of important information. One is detection, whether a signal or an event exists or present. 2, classification, what type of signal or event it is. 3, localization, exact start and end time of the signal. Okay, experimental results and analysis. Okay. We set up our experimental. This is some examples. First, for seismic signals. This signal is from the.
Yeah, you need to close to the microphone.
This signal detection example is from North Korea nuclear test. We can see the results. Bounding box under its class and start and end time. And it's on the upper corner. It is the probability. Very high. This is a detection of seismic signals from India. These exploring signals are very famous in our research circles. And this is an unclear explorer from Pakistan. It is an earthquake. We can see the bounding box and the probability. And this is the PR curve, precise and recall. And this is our experimental results. Significant performance improvement across all metrics. Now, I give some examples for infrasonic signals. This is a mining exploring detections. The signal is too low to identify. This is another detection examples. From rocket launching. And this is a blind, our key signals, blind exploring. After detection, we calculated the slowness and give its back azimuth. And then intersect the point of the source.
If you can go to the conclusion.
Oh, okay. Conclusion. What we do? We introduced a novel paradigm shift. From one-dimensional signal detection to two or three-dimensional computer vision task. Okay, because of time limited, I introduce the future work briefly. We just apply this method on unlimited data. In the future, we will apply it in amount of data, and we will train molten models with experts, because the AI models do the work in a black hole or a black box style. We can use the AI to do the future extraction work and use the export system to make the decision.
Okay. Thank you.
Okay.